Okay, so today we're going to continue our discussion of the multiple linear regression model. So last time we reviewed some properties of vectors and matrices, and I showed you the multivariate normal distribution, at least some of the key facts about it that will be useful to us as we continue to explore linear models, and specifically in this case we will see how the multivariate normal is going to be immediately applicable as we look at estimation and inference for multiple linear regression. So let's recall a couple things. So first is in matrix form we can write our model for the response y. When in multiple linear regression we have a matrix with all the x values, as we defined last time, multiplied by the vector of coefficients beta, which we will estimate. So today we'll talk about how to estimate all the parameters in beta. So how many are there? Well, we're assuming we have p predictors and then plus the intercept term. So beta is a p plus 1 length vector, and then plus epsilon. Okay, which accounts for any the fact that this model likely is not a perfect description of the data, and so epsilon captures any variability that's not captured in the regression part of the model. Okay, so recall that we said, okay, so epsilon is a vector. So we said in the usual regression setting, all the epsilons, so previously we wrote it like this, right? So all the epsilon i's are IID normal 0 sigma squared. Okay, so since we're going to adopt matrix and vector notation, well, let's talk about how we can rewrite this assumption on the epsilons in terms of what we learned. Okay, so we know that all the epsilons have the same variance, sigma squared. Okay, so imagine the random vector. So the random vector okay, and we'll see that we can write the vector. Oh, thanks. Excuse me. This is epsilon. The random vector epsilon can therefore be written as a multivariate normal distribution. Okay, so let's see how. Okay, so we need multivariate normal. So I need to specify a mean vector and a covariance matrix. Okay, so the mean part of multivariate normal. So remember, in vector form, each of these entries represents the mean of each epsilon I, so we know that they're all 0. Okay, so that's mean vector. And then in the covariance matrix, let's remember what we said about the properties of the covariance matrix for especially in the case of multivariate normal. So remember, the diagonal elements are the entries for the variances of each epsilon I, so all of them are sigma squared, so all along the diagonal we have sigma squared. Okay, so all the diagonal elements are sigma squared. And what about all the remaining elements? Okay, so we stated a fact about multivariate normals, and that is when they have 0 covariance, then they're also independent. So in fact, we can write this statement about independence, and it can be expressed succinctly in this covariance matrix. All we need to do is put zeros in all the off-diagonal elements, and that is equivalent in the special case on multivariate normal of encoding independence. Okay, so here the 0 means that epsilon 1 and epsilon 2 have 0 are uncorrelated, 0 covariance. And by the facts of multivariate normal, they are also independent. Okay, so basically everything in here is 0. Okay, so therefore we have taken this assumption about the normal for the normal distributions for the errors and encoded that as a multivariate normal, single multivariate normal distribution. Okay, and so dimension. Okay, so remember we're assuming about n data points. So mu is an n by 1 matrix, and then or column vector, and then sigma. So we use cap sigma to denote the covariance matrix. This is an n by n matrix. Okay, and so we can write this more succinctly as follows. Okay, so this 0 vector. So we can just write. A 0 as a vector. Okay, so remember this one is n by 1. And then we can write the sigma as the covariance matrix sigma as sigma squared. Okay, so if you look at this form, this is pretty close to identity. All right, just factor out sigma squared, and then you will have all ones in the diagonal. So it's simply the constant sigma squared times the identity matrix, which I'll write as I. And so remember, this identity matrix here is specifically the dimension n by n. Okay, so that's helpful because then we can write this entire condition where the epsilon i's are ID, normal 0 sigma squared from 1 to n is equivalent to this statement here. So these two are saying exactly the same thing. So these are equivalent. Okay, so this statement is helpful because then we can do all of our other computations in terms of vectors and matrices. Okay, so y. Okay, so let's go back to y now. So the random vector y is the regression part plus the error part, and so we put that together with this statement. So then we know, therefore, the random vector y has a multivariate normal distribution. Okay, so x beta is a constant part. So multivariate normal is coming from the epsilon. Okay, so we're just shifting the mean by x beta. Okay, so that means y's mean is x beta, and then the covariance matrix is coming from epsilon. Okay, so that's how we can capture the regression assumptions very succinctly by writing the whole multiple linear regression as a multivariate normal distribution. So just to make sure we don't miss this point, so let me just emphasize here. So remember, this guy captures the fact that covariance epsilon 1, epsilon 2 is 0, and in this case is independent. And then these guys, so for example, this guy is variance epsilon n. Okay, so both the variance and also the independence is captured in this covariance matrix. Okay, so now we're ready to estimate beta, and we're going to do it very compactly using matrix notation. But first, we need to define. Let's define our objective function. So what do we minimize? Okay, so just like in simple linear regression, we're going to take the least squares method of estimation. Okay, so let's first write down the least squares expression that we want to minimize, so you can see the connection with simple linear regression. Okay, so least squares. Okay, so let's define the objective that we want to minimize. Okay, so I called it S back then, so I'll use the same notation. So the objective, what are we minimizing this as a function of? Well, now instead of just beta 0 and beta 1, we have p plus 1 parameters, beta 0. So we have beta 0 for the intercept, beta 1, the first predictor, up to beta p for the p explanatory variables we have. Okay, so now we're going to minimize it as a function of all the betas. And the expression is analogous to the one we used for simple linear regression, except we just now have p explanatory variables. Okay, so what's the expression? Well, we take, okay, so what are we taking? We're summing over all the observations, and then we're minimizing the difference between the values we observe for the response and what would be predicted using the regression part, x beta. Okay, so I'm going to write this in the, so you can see the connection with simple linear regression first. So we'll take, I'm going to take the ith response and then subtract the regression part. So we're fitting this model, beta 0 plus beta 1 x I1, okay, for the value of the first explanatory variable for the ith observation, up to beta p x I p. Okay, so that's the difference between the response and the regression part that we're going to fit to the response. Okay, so we're taking the difference, yi minus the entire regression part, and then square, and then sum over all the observations we have. So you see this is analogous to our simple linear regression expression, except instead of just beta 0 and beta 1 x, we now have p terms for all the different x's. Okay, so I'm going to write it this way, so you see it's just an extension of the simple linear regression objective function. Okay, and so just like in that case, we call, so this part, so this regression part is, remember this is the expectation of the random variable for yi, right? And so we can call this, just like last time, we can call this mu I for short, to denote the modeled mean for the ith observation. So this entire regression part, beta 0 plus all the betas times the corresponding x variables. Okay, so once we have that set up, then we proceed very similarly to how we got the estimates for simple linear regression case. So first thing we're going to do is take the partial derivatives. Okay, we're going to find the critical point for this function s. So that means we take the partial with respect to each of the betas. Okay, and so actually most of the forms look the same. So let's write the first one. So let's take the derivative. So partial s with respect to beta 0. Okay, and I'm going to use mu I for short to represent this whole regression part here. So we don't have to keep rewriting it. Okay, so we're going to take the derivative. So we have summation. So the chain rule, so 2 comes down. Inside we have yi minus the regression part, so mu I. And then we need to take the derivative of the inside. So with respect to beta 0, then everything is constant with respect to beta 0 except this term here, minus beta 0. So we have a minus 1. Okay, so that's the first partial. And then we can observe that, in fact, all the other partials have a very, very similar form. So I only need to write it once. So let's do the partial with respect to beta j. Okay, so j is any of these predictors. Okay, the reason is we see, okay, so we apply the partial. So we have 2, okay, we have yi minus mu I again. And then we have the derivative of the inside part, and we notice no matter which beta you're taking the partial with respect to, what's left is minus the corresponding x next to that beta. Right? So with respect to beta j, then what's there's only one term that's left, and that's minus x ij. Okay, so it's pretty compact. We only need to write it once, and this holds for all the predictors j from 1 up to p. Okay, so all of these p partial derivatives have exactly the same form. Okay, so now we have overall we have p plus 1 equations. Okay, and then just like in the case of simple linear regression, we set these partial derivatives to 0, and then we solve. Okay, so let's do that here. So we're going to set all these partials to 0. Okay, so what are the equations? Okay, well let's simplify a little bit. So we can throw out the constants here. So that means we have these equations. So we summation yi minus mu I equals 0, and then here I can throw out the minus 2, so we have yi minus mu ix ij equals 0. Okay, so the estimates will be the solutions to these p plus 1 equations. Okay, so the reason I wrote it like this is now we can re-express this in vector form. So then we can solve it as a linear system. Okay, so you see this is you can view this as a linear system in terms of with p plus 1 unknowns, so beta 0 up to beta p, and p plus 1 equations. Okay, so let's rewrite the first one. So this is a summation of all the yi minus the regression part. So remember, mu I is the entire regression here, beta 0 up to beta p. Okay, so in compact vector notation, you can imagine each of these y. So you're doing y1 minus mu1. Okay, you can multiply by 1 if you like, and then plus y2 minus mu2 times 1, and so on. So the reason we can think of it that way is we can rewrite this as a vector dot product. Okay, so that can be expressed as a vector of 1s, as I was explaining. So we can think of this as a vector of 1s times y minus mu as a vector. So with y minus mu. Okay, so this equals 0. So that is that re-expresses this summation as a vector, as a dot product of two vectors. Okay, so usually what I mean here is the vector of 1s, so I need to transpose, so we get the notation clear here. Okay, and so we can do this similar thing for the second equation. So we can rewrite that as a dot product as well. So okay, so let's remind ourselves where this x part comes in. So remember, our x matrix looks like this. Okay, so we have a column of ones, and then we have x11, x12 up to x1p, and then this goes to xn1, n2 to xnp. Okay, so we're going to write this as a bunch of column vectors. So we can do this. Okay, so I'm going to write each of these. I'm going to define this notation. The first column is exactly the same thing as this vector of ones. So this is n by 1. Okay, and then I can similarly define vectors. So I'll call this next column. So this is the first column, and then we have x1 as a vector. So that refers to the second column of this matrix, and so on. Okay, so each of these x vectors stands for the corresponding column in this matrix. So with that notation, then this can be expressed as our vector dot product between, well, the corresponding the jth column and y minus mu. Okay, so this is xj as a vector. Okay, so this is in column form, so transpose first, and then multiply y minus mu. Okay, so we have this equation for j from 1 to p. And so we have our setup necessary to give the entire linear system can be as solution to the following equation. So you notice that in fact, so we just need one more step here, is to notice that in fact this vector of 1 is exactly the first column up here of the X matrix. So in fact, this entire thing can be written as, you can think of the X matrix as capturing the ones and then all the X's. So we can even compact all of this together, and by observing that the matrix X has all of the corresponding columns, so we can write the entire thing as just a matrix multiplication. So combining these p plus 1 equations. Okay, so all we have is just X transpose times y minus mu equals 0. Okay, so this is the equation, then that gives us the least squares solution. Okay, so this gives the least squares solution for beta. Okay, so let's solve this, and then we will have our beta hats, just like in simple linear regression. Okay, so let's first first make substitution. So remember, let's put back what mu is. So x transpose y minus, so mu, recall, is x beta. So that equals 0. Okay, so let's multiply through. So x transpose y minus transpose x beta equals 0. Okay, so we move it to the other side. So beta x transpose x beta is equal to x transpose y. And so recall this whole thing, x transpose x is a matrix. So we multiply by its inverse on the left hand side, on the left side. Then that will give us the identity and leave us with the solution for beta. So therefore, beta x transpose x, the inverse is, and x transpose times y. Okay, so that is the matrix algebra based solution for the least squares, and so it's very compact. Now, of course, whether this works depends on the fact that this matrix x transpose x is invertible. Okay, so we should state that. So under what conditions is this invertible? Well, there's many different ways of expressing that. So you could say it's x transpose x should be a matrix of full rank, or equivalently, it has linearly independent columns. So those are the characterizations which would be useful to note here. So okay, so let me write here. So the least squares estimates is given by. Okay, so now that we've solved least squares equations. So we have beta vectors. So the hat of that is x transpose x inverse x transpose y. Okay, so assuming that if x transpose x is invertible, so we can say it's full rank equivalently. So what's the full rank in this case? Well, this is a p plus 1 by p plus 1 matrix. So full rank is of p plus 1. Or equivalently, another useful way to think of it, which has a practical notion, is that the columns are linearly independent, or so linearly independent columns. So that says that you cannot express. Okay, so if all the columns are linearly independent, then you cannot express one of the x columns in terms as a linear combination of the others. And so why is that reasonable in a regression context? Well, if you can express one of your explanatory variables in terms of the other ones, then you don't need that explanatory variable. Okay, so this assumption will be satisfied as long as we properly screen our explanatory variables so that we don't have any redundant variables, in the sense of you can express in the sense of being able to express one of them in terms of the others. It would not be useful as a predictor in any case. Okay, so we would be later, as we talk about some of the practical implications, and when we look at, for example, how to select variables to use in our regression, we often do check for correlation among the predictors themselves. Okay, and so we would be able to check in any practical usage of this model that we have an invertible X transpose X matrix, because we can screen the X's and decide which ones to include in our regression. Okay, so as before, let's now move on to the residuals and also the estimates for the residual variance, sigma squared. Okay, so as before, let's define the residuals. And the residuals, of course, are defined in terms of the fitted values. Okay, so define the residuals. Okay, so again, I'm going to use EI here for the values. So these are calculated on our data. So it's the difference between the response and what and the fitted regression part for the response. Okay, so we have beta 0 hat, beta 1, xi1, beta at p, x at p. And just like before, we can call this part our fitted value. And I'm going to use the same notation, so mu I hat. Okay, and so when I write beta 0 hat, beta 1 hat, it should be clear that we're talking about all the p+1 entries of this vector beta hat. Okay, so the residual can therefore also be written in vector form. So, or equivalently. Okay, so how do we get this one? Well, we take the value the mu hat as a vector would simply be to take x times the least squares estimates, x beta hat, okay, or and so the vector of residuals e would be y minus mu hat. Okay, so that's the residual, and then we also need the estimate of the residual variance, that's sigma squared, and so we have the residuals, and then we estimate the sigma squared based on the residuals, based on the EIs. So that gives us sigma squared hat. Okay, so now let's remember how we got sigma squared hat in the simple linear regression case. So on the top was a sum of square residual. And then on the bottom was when we had one predictor and an intercept, it was n minus 2. So we also call this the degrees of freedom. And so if you recall, when we talked about that, we said it was n minus the number of estimated model parameters. So in this case, there are p plus 1 of them. So let's highlight that here. So this is degrees of freedom, which is n minus the number of estimated parameters. Okay, so sum of square residual. Well, in our notation, remember it's just the summation of ei squared, bottom e of n minus p minus 1. And also, just to get in the habit of writing things in more so in vector form. So this is the dot product of the e vector with itself. So that's e transpose e n minus p minus 1. Okay, so that is the corresponding estimate of the residual variance. And okay, we'll say one more fact. And likewise, it has a when viewed as a random variable, sigma squared hat, when viewed as a random variable, is related to the chi-square distribution, just like in the simple linear regression case. So in this case, the degrees of freedom is n minus p minus 1. So we put n minus p minus 1 times sigma hat squared as a random variable, divided by the true unknown value of sigma squared. So this is chi-squared n minus p minus 1. Okay, so it's the corresponding result. You notice when you have one predictor, that's simple linear regression, so you plug in p equals 1. That's the result we stated when we looked at that case. So this is the chi-square related to sigma squared hat viewed as a random variable. Okay, so we have our estimates for beta. So our next step is to look at inference. Okay, so specifically we're talking about the inference for the estimate beta hat. Okay, so remember this is a vector of estimates, so beta 0 hat, beta 1 hat to beta p hat transpose, which is obtained as x transpose x inverse x transpose y. Okay, so I'm going to switch to the random variable because we're going to look at the distribution of beta hat. Okay, so we're going to follow a very similar pattern as when we did simple linear regression. We're going to look at the mean and variance of beta hat as a random variable, and from there we are going to follow the same pattern, derive the corresponding distributions, so we can get confidence intervals, and then do hypothesis testing on the parameters. Okay, so as a random variable, note that beta hat vector is okay. So what is its form? Okay, so you notice it's this matrix. You can think of it as this matrix, so times the random vector y. Okay, so what is this? Well, x's, remember we were assuming all our x's are known constants. So all this stuff it's simply a matrix of constants. So it's, in essence, beta hat is a matrix of constants times a random vector y. And what is the distribution of random vector y? Well, it's multivariate normal. Okay, so now we see how the facts we talked about in terms of multivariate normal are going to be useful here for deriving the distribution properties with beta hat. Okay, so let's head in that direction, but let me first note that beta hat is a matrix of constants times y, which is a random vector. And specifically, y as a multivariate normal with mean x beta. So this is the true unknown beta, x beta, and then variance, covariance matrix, sigma squared identity. Okay, so now we can use facts about random vectors and multivariate normal to derive the coordinate distribution for beta hat. Okay, and so it follows that. Okay, so let's work out these expressions. Okay, so let's calculate the mean of the random vector. Okay, so let's work through what this is. So let's plug in its definition. So we have x transpose x inverse transpose y. Okay, and then use our rules. So this whole part is a constant, so I'm going to pull that outside. And then we have e of y. The e of y simply comes from the mean of this multivariate normal. And it is x beta. Okay, and so now all we have to do is we need to let's put brackets here so that we can see that the x transpose x, group it in this way, and we see that this cancels, and you get the identity times beta. Okay, so the mean vector of random variable beta hat is the true unknown betas. So in other words, what we're saying is that all of the betas are all the estimators for the corresponding betas are unbiased. So if I were to take the expectation of beta 0, that's beta 0, and so on. Okay, so all the so the beta estimates are unbiased. Okay, so our next step is to take the variance. So again, we'll get some practice using the rules that we talked about last time. Okay, so again, this is the variance of x transpose x inverse, x transpose y. Okay, and we apply our rules for variance. Okay, so this again is just a vector. This entire part is a vector. A matrix of constants. Okay, so we're going to so we have variance of matrix A times y. Then we're going to have A variance y and then A transpose. So that's exactly what we'll do here. Okay, so on the outside we have x transpose x inverse x transpose. Okay, and in the middle is variance y, and then on the other side is the transpose of this whole thing. Okay, and so now we can start simplifying. So we copy this first part down. Okay, variance y. So according to the model setup for random vector y, its variance is sigma squared times the identity. So we can plug that in. And then we take the transpose of this expression. Okay, so this is like A, two matrices, A times B, all transpose. So we flip the order, so we have X transpose transpose. And then we have the transpose of this inverse. X inverse transpose. Okay, and so let's simplify this. So we have X transpose X inverse X transpose. Okay, and then with the sigma squared, it is just a scalar constant. So I'm going to put it outside. Okay, so sigma squared is not a matrix. It's just a constant that's multiplied on the matrix. Let's put it outside. X transpose is just X. Okay, so you notice we're gonna put a bracket here again, so then we cancel off the X transpose X inverse. And finally in here, we notice that X transpose X is by construction is symmetric. And so, okay, so the transpose of it is the same thing, so we just need X transpose X inverse. Alright, so now this part cancels, it's the identity. And so we have the variance of beta hat sigma squared times the inverse of X transpose X. Okay, and so beta has this mean and this variant, but what we can say additionally about beta is because it is simply a linear transformation of a multivariate normal. Okay, and so we learned that linear transformation of a multivariate normal is still a multivariate normal. So in fact, beta, our estimator beta hat, has a multivariate normal distribution with this mean and this variance. Okay, so we have our distribution for and beta hat is a linear transformation of y, and so it is multivariate normal with this mean and covariance matrix. Sigma squared X transpose X inverse. Okay, so mean vector beta and covariance matrix. Okay, so so let's just call, for simplicity, let's call this guy, let's just call it B. And what follows. Okay, so we have the joint distribution of all the betas. So from this distribution, we can talk about specific betas. Okay, so we can ask, is beta 1 significant? Is beta 2 significant? And so on. And so we have a convenient way then of getting all the information we need for confidence intervals for specific parameters and hypothesis testing for specific parameters. So let's show you how to do that. Okay, so now for a specific parameter, Okay, so we look at beta j, for example. Okay, so a fact we stated about the multivariate normal last time is that the marginal, so you take any individual component in this random vector, it will have a normal distribution with the mean and variance. You just have to take the coming from the mean vector in the covariance matrix. We just have to pull out the corresponding entry. Okay, so for example, beta j. So beta j hat would have a normal distribution. Okay, so we would have the jth entry of the mean vector, so it's beta j. And then, as we said, the variance of beta j hat would come from the jth entry of the diagonal of this matrix. Okay, so it's going to be sigma squared times, so that's why I'm using the shorthand. So take the matrix B and then take the jth entry in there, and that would give us the variance for the marginal. Okay, so this is from the marginal property of the multivariate normal. Okay, so this is the jth entry of B. Okay, so once we have that, now we're back into the one dimension case. So now we're dealing with just one parameter at a time. So beta j, the estimator has this normal distribution, and so we can do the usual things we do. So for example, we can standardize. So beta j minus the estimator minus the mean, beta j, divide by sigma square root of bjj. Okay, so this is going to have a standard normal. In practice, we don't have sigma, so we replace it by its estimate. So we put sigma hat bjj. Okay, so this in the simple linear regression case we know has a t distribution. Okay, and then the degrees of freedom is coming from the degrees of freedom we talked about in the chi-square for the residual. Okay, so by replacing sigma with the estimate, normal becomes a t, and degrees of freedom in this case. Okay, as we wrote down, it's not here anymore, but we wrote down the residual degrees of freedom is n minus p minus 1. Okay, and then again for shorthand, we call this guy. Okay, so this thing is a standard error of beta j hat. Okay, so we have all the ingredients now to do our hypothesis test and make confidence intervals. Okay, so let's write them here. So a 1 minus alpha confidence interval for beta j is beta j hat. So this is very similar now to the simple linear case. So we can do for each individual parameter, we can construct a corresponding confidence interval. Okay, so this follows exactly the same logic as, well, we only had one. Okay, so beta j hat plus minus a constant, which is going to come from the t distribution times the standard error of the estimate. Okay, where C is defined the same way, is the 1 minus alpha over 2 quantile of this t distribution, n minus p minus 1. So what's worth pointing out here is, well, each of the regression parameters will have its own estimate and its own standard error. And so later, as we start applying it in practice, we'll see that the standard errors, of course, can vary a lot from parameter to parameter. It may turn out that some of the predictors are significant and others are not. Okay, and that's what this analysis will show us when we apply it on specific examples. Okay, so that's confidence interval, and to test the hypothesis, beta j equals 0 versus not 0. Okay, so it's same as before. We calculate the t statistic, so we calculate t statistic okay, so we take estimate for beta j, divide by its standard error. Okay, so we'll be talking about the same significance level, so reject at level alpha if the absolute value is greater than the critical value, so it's the same C, so it's the same guy here. So. And finally, the corresponding p-value, we can calculate p-value is, okay, so we'll just write it as 2 times probability random variable t greater than or equal to this value t from the calculated test statistic. And then this is the t distribution with n minus p minus 1 degrees of freedom. Okay, so all of that is pretty much analogous to the simple linear regression case. So once we've worked out the matrix form of our estimator, we can take the covariance matrix, and from there we can go back to the 1D, looking at the parameters one at a time. And so once we're looking at parameters one at a time, then we have all the tools from before. We apply the same tools to get the confidence interval and to get our hypothesis test. Am I missing a division sign for the first thing that follows a normal? Let me see here. My bad. So okay. So yes, thank you. So I'm calling V this entire thing, and so this is sigma times root Vjj. That's right. And then this I accidentally wrote a division sign here because from the way I defined the notation, we're talking about root Vjj. Yeah. So these two should be the same. Thank you very much. Okay, any other questions so far? Let me know in chat. Okay, so last thing I want to mention today is interpretation of the estimated coefficients. Okay, so again, correct your notes here. We based on the notation, the way I define it, this standard error is sigma hat times root of EJJ. Okay, so interpretation of our betas. Okay, so again, this is an extension of the interpretations we made in the simple linear regression case, and there's a couple things we need to be careful of here, but mostly what we said there maps over. Okay, so first let's talk about the fitted regression model. Okay, so our fitted multiple linear regression model says that the okay, so I'm gonna write it this way. I'm gonna put E of, okay, so slight abuse of notation, but I should get my point across. So we're estimating the mean of y. That's why I'm putting a hat over the entire E of y. Okay, so in words, what I'm talking about is with the estimate. So this whole thing is the estimate of the expected response. Okay, so that's what I mean. Okay, so writing it this way to help us do interpretation for the coefficient. Okay, so the estimate of the expected response is this regression component. So beta 0 hat, beta 1 hat, x1 up to beta p hat xp. So if I give you values for each of the x's, there's p of explanatory variables. So if we have values for all of them, then this would be the fitted model for the expected value of y. Okay, so that's what we mean here. And the reason I write it like this is so we can do interpretation. So beta. Okay, so let's start with beta 0. Okay, so what's the meaning of beta 0? Well, when all the x's are 0, then beta 0 tells us the expected response for y. So again, that depending on the application, that may or may not have an interpretable meaning. But from a modeling point of view, this is what beta 0 hat denotes. Okay, so it's right here. So beta 0 hat is therefore the estimate of the expected response when all the explanatory variables are 0. Are equal to 0. And for the rest, we can interpret them similarly to the slope parameter we had in simple linear regression. We just have to be a little bit careful to say that the interpretation is assuming that everything else is held constant. Okay, because now we can have multiple x's in our equation. Okay, so let's start the same way as before. So this is the estimate. Beta j hat is the estimated change of the change in the expected response okay, so so if I increase the corresponding x by 1, so xj, if I increase xj by 1, then this is beta j hat is the corresponding change. Okay, so for a unit increase in the value of xj. Okay, so far this looks exactly the same as with simple linear regression, but now because there's multiple predictors, we have to add another clause, is that this interpretation only makes sense, of course, when we hold all the other x's fixed, and you don't change the other x's. Okay, so we need to add this clause when holding all other explanatory variables constant. Okay, so this part is something we have to add now in our interpretation, and this part is required so that the interpretation here only makes sense when we don't change the other x values. Okay, so holding all other explanatory variables constant. So I mean, just to make it clear, so for example, if I increase x1 by a unit while leaving everything else fixed, okay, so if I do beta 0 hat plus beta 1 hat, so I take the value of x1 and I increase it by 1 unit, so x1 plus 1, and leave everything else the same. Beta hat p plus p, okay, minus the same thing, but at the everything else at the original values. Okay, so the only change in these two expressions is I've added 1 to the value of x1, so you see after subtracting, the only thing you're left with here is beta 1. Okay, so mathematically that's how we can see clearly why this is the correct interpretation. The expected change in the estimated change in the expected response, and then this difference is exactly the parameter we have estimated, beta 1, and so the same logic applies to any of these parameters from j. J is anywhere from 1 to p. Okay, so I think it'd be useful to do a really quick example, so it should take just maybe about 5 to 10 minutes. So let's, yeah, so I'm going to do this example while I still have this picture of our space shuttle here. Okay, so going back to this example, we had two predictors, nozzle area, so that's categorical, large or small, and then our second predictor is the propellant ratio. So we'll call those x1, x2, and our response is the thrust. Okay, so we'll call that y. Okay, so I'm going to just give you some summary statistics so you can see how this works out. And later we'll in one of the coming lectures, I will show you how to do this sort of analysis in R. For now, let's just look at it numerically on the board. Okay, so let's go back to our rocket example. Okay, so let's give you some summary statistics. So I had 12 observations in the data, and after computing my estimates, so beta hat, the vector is, okay, so there are three betas in this case. There's the beta 0, okay, and then we have beta 1 and 2 for the two predictors, x1, x2. So my vector of parameter estimates came out to be, okay, so 470, so we take this as given for now, 473.6 minus, 16.7 and minus 1.09. Okay, so this is talking about our three estimates, beta 1 hat, beta 0 hat, 1 and 2. Okay. that's our parameter estimate. And then we also calculated our estimate of the residual standard deviation. So that's the square root of the estimate of sigma squared. So conceptually, what we had to do is add up all the squared residuals. So on top is sum of square residual, and on the bottom is n, so 12, and then minus the number of parameters we estimated. So the intercept plus the two slope parameters, so 1 and 2. Okay, and then I did this in R, and I got 2.655. Okay, so let's take everything here as given. And let's interpret. Okay, so it's here. So according to this model, then okay, so let's look at 1 hat. Okay, so in words, for this particular example, so beta 1 hat, so that's 16.7. So what is this? This is the estimated change in the expected thrust is 16.7 units. Okay, so what changes in this case? So beta 1 is associated with x1. So what is this? This is the expected change when you go from a small nozzle to a large one. Okay, so make sure we interpret it in the appropriate context. Changing small to large. Okay, and then let's use the phrase we had before. In this case, we need to hold the other variables constant. In this case, there's only one, so while holding other variables, in this case, we can actually write it as the propellant ratio constant. Okay, and then in a similar way, beta 2 hat says we can interpret it as follows. So beta 2 hat is this coefficient minus 1.09. So we estimate the thrust as to decrease by 1.09 on average. Okay, so I'm purposely writing it a slightly different way because there are different ways to express the same idea. So we estimate the thrust decrease on average by 1.09 for a unit by increase in the propellant ratio. Okay, and then again while holding the variables constant. Okay, so when I ask you to say interpret a coefficient, so make sure you, similar to this, you reference the specific scenario. So make sure you mention the response and the specific predictor. So that we can interpret it to non-statisticians and can be understood by non-statisticians as well. Okay, and all right, let's give you one other piece of information, and then we will do a quick hypothesis test. Okay, so given, suppose I tell you the standard error of the beta 2 estimate is 0.94. Okay, so what conclusions can we draw about the parameter beta 2, or in effect the significance of propellant ratio as a predictor of thrust? Okay, so let's quickly do what we did for confidence intervals and hypothesis test. Okay, so then we can say the following. The t statistic for testing the null, which is beta 2 equals 0, versus the alternative beta 2 not equals 0, is, okay, so the estimate is minus 1.09, standard error 0.94. So this is about minus 1.16. And so the p-value would be the probability that a t random variable exceeds 1.16. Okay, I'm going to take off the absolute values of 2, where t is, okay, so what's the reference distribution? We have 12 observations and we estimated 3 parameters, so we're looking up this value from t with 9 degrees of freedom, and so this turns out to be about 0.275. Okay, so this part is from R. And so we can state in conclusion that this p-value is quite a bit larger than 0.05. So we can conclude we do not reject the null hypothesis. Okay, so for example, if we're taking, for example, alpha to be 0.05, and conclude that propellant ratio does not significantly influence our response, which is thrust. Okay, so I think that's sufficient as a quick illustration of some of the concepts we talked about. So we will do the full analysis in R in one of our upcoming lectures, but I think a quick numerical example should be helpful, both in terms of interpretation and also carrying out the corresponding hypothesis tests for significance. Okay, so I will pause for a few seconds and see if there's any questions in chat. Okay, so I don't see any. So just a reminder, your second quiz will be posted after midnight, and so that will be based on not today's lecture, but the 2 lectures before it. Okay, there is a question. Linearly independent columns. Yes. So in order for the the least squares equations to be solved in matrix form, we need to be able to take the inverse of x transpose x. And so the inverse exists when the columns of that matrix are linearly independent. And so in practice, what this means is that you cannot express one of the predictors as a combination of the others. And so, in other words, at least we choose our predictors so that there is at least the possibility that each of the x's can potentially explain some of the variability in y. So we had if we define, for example, you have x1 and x2, and then we accidentally threw another variable x3, but x3 is simply like x1 plus x2, then that does not actually give any new information for predicting. So if you have x1 and x2 in the model, you don't need x3 if x3 is simply x1 plus x2. So those three would not be linearly independent explanatory variables. Okay, why do we have 9 degrees of freedom? So n, so the number of observations was 12. Okay, so I wrote it. I think I wrote it on the previous board. And here we estimated 3 parameters. We have beta 0, and then for the intercept, and then we estimated the 2 regression coefficients, beta 1 and beta 2. So we estimated 3 things. So 12 minus 3 gives us 9 for the degrees of freedom here. Okay, good. So we will see you on Monday, where we will continue looking at some of the properties associated with multiple regression. So we'll see you guys then.